Well, thank you very much for putting together this conference and letting me speak about this project. So this is joint work with Kuei Nguyen Lin and Gabriel Sosa. And I'll first start with where these kind of algebras start to appear. So in the process of blowing up, actually, we see Ries algebras appearing. So let's say we have a variety V and we have a subvariety W. And let's consider the coordinate ring of V and then the coordinate ring of that subvariety W. So when you blow up V along W, what you obtain is the product of this graded ring, R of I. So this ring is called the Ries algebra and it's defined as a direct sum of powers of this ideal I. And we have this variable T to keep track of the grading at each step. And we have this picture here. So when you look at the first picture on the upper right corner, this curve has a singularity at 0, 0. So the way to resolve it is by blowing up R2 at the origin. So when you blow it up, you get this space here, and then you kind of move along your curve, and then you resolve the singularity by looking at the intersection, right? So the blow up of R2 at the origin is actually corresponding to this object. So what we see here is R2 is like this polynomial ring KXY, and we're blowing it up along the variety corresponding to XY. So this algebra we see here is the Ries algebra of the ideal XY, actually. So this is just one example. So the Ries algebras appear when you blow up a variety along a subvariety, but this process could be done successively and you could blow up your variety along subvarieties. And in that case, the algebraic object whose product we take is the Maltese algebra. So let's say we have this commutative ring S, and then we have a collection of ideals, and we blow up along the varieties corresponding to these ideals. And then the Maltese algebra is defined in the same way that we define the Ries algebra. So for this collection of ideals, we take the direct sum of the powers of this collection of ideals. And this time we have R ideals. So we will have R many bookkeeping variables to say which ideal is appearing at which degree so that we know each one's contribution. And you see that this lives inside this extended polynomial, extended ring S with those auxiliary variables added to it. So I'm going to use this notation when I talk about the Maltese algebras of a collection of ideals, because it turns out that the Maltese algebra of the collection is the same as the Ries algebra of this direct sum module. Okay, so when one wants to work with the Maltese algebras or Ries algebras, this like direct sum definition is not very efficient. So we want to work with the defining ideals of these objects. So the defining ideal of the Maltese algebra is defined in the following way, but here I'm just going to focus on the kind of object that I'm going to work with for the rest of the talk. So we're living in a polynomial ring and n variables, and my collection of ideals are going to be monomial ideals. So then for each of these ideals, let's consider a minimal generating set. And then let's put all of those generators in like this gigantic minimal generating set of all these ideals from I1 up to IR. One condition we have in our setup is we want I1 to all the generators of I1 to be in the same degree. I2 and I1 could have different degrees, but I1 is all in same degree. So then we define this S algebra homomorphism by first extending our polynomial ring S by adding these new variables, capital Tij's. So for each variable we have for the ideals in the collection, so which we're picking from this big set G, we create a new variable, capital Tij. And then, so this is our domain. The codomain is this polynomial ring where we added the bookkeeping variables. And the map is defined in the way that you would expect it to be defined. So we're sending these capital Tij's to the generator that it was associated to times Ti so that we know this Uij is living inside the ith ideal. So we want to bookkeep all these things along the way. So it turns out that the Ries algebra, the Maltese algebra of this collection, is the image of this map. And as a result, you can show that, I mean, we know that we have this quotient ring where this kernel is the defining ideal of the Ries algebra. So in practical sense, when we want to work with this Ries algebra, we're working with the kernel of this S algebra homomorphism. So this is going to be our object of study, actually. And there's a related, nicer ring, which is called a special fiber ring. And it is defined as the tensor product of the Ries algebra with the field K. These are as S algebras. So the defining ideal of the special fiber is actually coming from, like, you restrict your coefficients in the domain to only the field, and then you have a toric map here. So the kernel of this toric map is the defining ideal of the special fiber. Okay, so these are the two ideals that I'm going to work with when I want to understand something about the Ries algebras or its special fiber. So the main question here is a very general question, is to find implicit equations for the defining ideals of the multi-Ries algebra and its special fiber ring. And I'm just going to use this fancy I for the defining ideal of the Ries algebra, fancy J for the defining ideal of the special fiber. While we're searching for implicit equations, we'll also keep this side question in our mind. We also want to investigate causalness while we're looking for implicit equations. So this is a very hard question to answer in the general sense, and people always focus on special classes of ideals because the definitions of those defining ideals heavily depend on the structure of the ideals that you work with. So in our case, we're going to work with strongly stable ideals. These ideals are very nice to work with, like computationally, combinatorially, they have a nice structure. And in characteristic 0, they coincide with what are called Borel fixed ideals. These are fixed under the Borel subgroup of triangular matrices. Also, generic initial ideals are of this type. Okay, so what is a strongly stable ideal? A monomial ideal is called strongly stable ideal. Whenever you have a monomial M in the ideal, you can replace a variable that divides the monomial with a variable of lower index. So that's what I mean by that here. So we have xi dividing m, but then we replace it with a variable with a lower index, and it should still stay inside the ideal. So the process of obtaining a new monomial by replacing one with a lower index is called a Borel move. So I'm replacing m with this one when these conditions are satisfied. So strongly stable ideals are closed under Borel moves. And here is an example. So let's think about the polynomial ring in these two variables. And let's look at this ideal generated by x1 square, x1, x2, and x2 square. So let's look at x2 square. From x2 square, I can replace one of the x2s with x1 and get this middle monomial. And then I could replace this x2 with x1, and then I would get x1 square. So this is obtained from x2 square via Borel move, and x1 square is obtained from this one via another Borel move. So all the generators in this ideal are obtained from this one through a sequence of Borel moves, and the same thing will apply to all the other elements, all the other monomials. So this ideal is strongly stable, but the second one is not, because even though we can obtain x1, x2 from x2 square via Borel move, it's not in that ideal, so it's not strongly stable. And we can use these Hasse diagrams to kind of see like what is like the minimal number of things that you need to create these, like represent these strongly stable ideals. So the monomials on top of these Hasse diagrams kind of tell you all the other things. And we will call those, like for this one, x2 square, we'll call that a Borel generator, because that's a minimal number of information to have everything else we need about the generators. So I'm going to use this notation B to talk about only the Borel generators. So this ideal I1 is Borel generated by x2 square. Okay, so when we study these multi-Ries algebras, they are complicated objects because there's so much going on. Like you have so many ideals, we need to control how many generators are there and what are the degrees, so they all play a role. So in our study, we focus on three sets of parameters. The first one is the number of ideals we have in the collection. The second one is the number of Borel generators for each ideal in the collection. And then lastly, we focus on the degrees of Borel generators for each ideal. And that's what people have been doing when they studied Ries algebra. So we kind of saw like what was going on and used this as our road guide to start working with these objects. So what is known? So we're in the Ries world first. In the Ries world, that first parameter is equal to 1 because you have only one ideal. So one of the early results in that direction is due to de Negri. So when there's only one Borel generator for a strongly stable ideal, she showed that the special fiber ring is causal, and she did this by finding a quadratic Grosvenor basis for the defining ideal of this ring. And she used this notion of sorting that was introduced by Sturm-Falz. So this is nice. And then in 2005, Herzog, Hibi, and Mladieu showed this really nice result, which kind of reduces the questions about Ries algebras to special fibers. And they showed that for a strongly stable ideal, doesn't matter how many generators, what the degree is, their Ries algebras are of fiber type. So fiber type means the defining ideal of the Ries algebra can be written in terms of the special fibers defining ideal plus the relations of the symmetric algebra. So these are linear forms in those new variables we introduced. So this is nice because if you want to study, let's say, causalness of this, you could maybe reduce it to causalness. You could obtain it from the causalness of the special fiber. So these coupled tells us Ries algebra of principal strongly stable ideals are causal. And then there was this example of Kunke and de Negri from early 90s, which was very nice because it helped us eliminate large classes of strongly stable ideals from having always causal special fiber rings. So let's look at this one. So this ideal is generated by these three monomials. These are Borel generators. And then they show that there is this cubic minimal generator of the defining ideal of the special fiber. And you can check that like this monomial squared times this one is equal to cube of this monomial. So that's where this syzygy is coming from. So when you have a cubic generator, it violates being causal because when you're causal, your ideal must be generated, the defining ideal must be generated by quadratics, but the other way around is not always true. So then what this example tells us is if you have 3 or more Borel generators, you might lose causalness. So you're not always causal. And then in this picture, okay, 3 and higher number of Borel generators are not always causal. 1 Borel generator is already known. So what is not known is 2 Borel generators. And it was addressed in 2018. There's a big gap since people like thought about taking care of this remaining case, and it was due to Di Pasquale, Francisco, Mermin, Schweig, and Sosa, and they showed that the special fiber of a strongly stable ideal and 2 Borel generators is causal, and then this result carries it to the Ries level. So in the Maltese world, there aren't that much known actually. This is the known collection of strongly stable ideals whose Maltese algebras and special fiber rings are causal. So one of the results is from 2013 due to Lin and Pollini, and they considered powers of the maximal ideal, homogeneous maximal ideal. This is like a subclass of principal strongly stable ideal. So it doesn't cover the whole principal strongly stable case. And then in 2014, Sosa extended their results to these principal strongly stable ideals satisfying some ordering condition, but it was still not the whole principal strongly stable collection. So it wasn't until 2020, right before we completed our project, Di Pasquale and Jabbar Nazad showed that actually the Ries algebra of a collection of principal strongly stable ideals are causal. Okay, so what are our results? So we try to mimic what we've seen was happening in the Ries algebra case. So we've seen the power of that Herzog, Hibby, and Vladieu result, which allowed people to just study the special fiber to say things about the Ries algebra. So the first thing that we proved is the multi-Ries algebra of strong and stable ideals is of fiber type. And what we actually proved is if you have a Grosvenor basis for the defining ideal of the special fiber, you can take its union with this set of quadratic binomials, and it forms a Grosvenor basis of the defining ideal of the Ries algebra. So this is nice because if you find a quadratic Grosvenor basis for this one, then you will have a quadratic Grosvenor basis for this one. And then causalness of the special fiber implies causalness of the Ries. So that was the first thing. And then we also tried to find some examples in the spirit of Conca and de Negri so that we would eliminate some large classes of strong and stable ideals whose causal algebras are, whose Ries algebras are not always causal. And I'm not going to show you the examples because there's a lot of data there, but if I were to just summarize what happened there, we just eliminate these kind of cases, by controlling those three sets of parameters I showed you. In the light of those examples, we created this potential collection of strong and stable ideals whose multi-Ries algebras are always causal. But I want to say that this is potential. Maybe you will find a collection that fits inside this table and maybe they're not causal. You might find more examples violating causalness, but this is what we were able to kind of clean up after those examples. I'm not going to get into the details of this table, but I'm just going to highlight the case that we consider as part of this project. So we're considering two strong and stable ideals, and each of them have two Borel generators, and they're generated in degree 2. So this is the case we consider after coming up with this table. So it's this case, right? And in that case, what we show is their Ries algebra is causal. So what's nice about the case of strong and stable ideals with two quadratic Borel generators, you can express them in this way, right? So you have two Borel generators. We have XA1, XB1 as the first generator and XC1, XD1 as the second Borel generator. And we have these nice ladder diagrams to work with when we want to study these things. So this Borel generator corresponds to this corner, and through Borel moves, you could get all the other monomial generators here. And that blue one is this corner, and through Borel moves, you cover everything to the left and up of this one. So the key idea in the remaining 2 minutes, I'll just try to give you the main idea of what we've done, how we proved this last thing. So I want to remind you that we had this toric map, now we're focusing on the special fiber. So for the generators coming from the first ideal, we use U and V for the second one. And then we have these new variables we create, T sub U, Z sub V. And then we extend our polynomial ring with T and Z. So the new variables that are coming from the generators of the first ideal are sent to the corresponding generator times T, and these ones are sent to VZ. So we find a quadratic Grosvenor basis for the kernel of this toric map. And our monomial order is what we named head and tail order. So these diagrams that we have were useful to come up with that term order. So first we order the variables of this polynomial ring by using the diagrams. So we order the T variables that are coming from here using the Revlex order. So we start at T11, and then we go to T12, T22, and then we continue in that pattern. So this is the Revlex order. But when we pass to the Z variables, when we started from here, it did not work. So we had to start from the tail, and then we start at Z1, B2, 1 plus 1, and then go this way, then jump to the head. So this is our variable order, and then the term order is the reverse Lex order on this ring induced by this variable order. And our Grosvenor basis, we can express it as a union of these three collections of binomials. So in this first one, what you see is it's actually a Grosvenor basis of the defining ideal of the special fiber of I1 with respect to reverse Lex. This is for the second one with respect to that head and tail order. This was known in the literature, but we use fiber graphs to show that. And this is the interesting part where like two variables, two ideals are interacting with each other. And our main tool is what we call a fiber graph. These fiber graphs we check them at each multi-degree. So if you remember, we had this toric map. We're looking at monomials in here. So we're going to have this multi-degree, and we look at the fibers of those monomials. So in the fiber graph, it's a directed graph. Vertices of this directed graph come from the fibers of the multi-degree under that toric map. And the edges are created by looking at that Grobner basis, the collection that we had. So we're testing something about this this fiber graph to check if this collection G is a Grobner basis. And here is just a picture to show you like how the fiber graphs look like. All these vertices are mapped to this multi-degree actually under the toric map. And then just to show why we have an edge between these two vertices, because the only things that are different is these two. So I'm kind of replacing this one with 3, 5, 4, 4, because the difference lives inside G3. So this is called a one-step reduction, like replacing parts of the things in V with things inside the second term in G3. So we create these edges. And we use fiber graphs because when these have a unique thing for every multi-degree, they give us that the collection that we started with is a Grobner basis. And I'm going to probably stop here. I'm over time. Thank you all. And yeah.
Okay, great. Let's thank Selvi. Very interesting. Questions for Selvi?